So we have an orthogonal basis, and then you have a transformation like rotation. So based on that, we said a vector will transform itself. So if you have a vector AI will go to AI prime, A prime I, which is equal to del x I prime by del xj into aj. Okay, so this is such vectors we called it as contravariant. And you have some vectors, let's say bi goes to bi prime, which is equal to del xj by del x I prime into aj. These vectors are called covariant. And once we understand this, then higher rank tensors can also be transformed in this fashion. For example, if we have a tensor of rank 2, for example, then you will say Tij will become T prime ij, which can be written as del x prime I by del x L into del x prime j by del x m into ALM, TLM. Okay, so you just have to write this. What is the rank of the tensor? So many factors like this you have to write. That is all that you have to do here. So this is the first thing that we have learned. And then we have used rotation to get this, get to this kind of a result. And second, we have discussed the non-orthogonal basis. Non-orthogonal basis. So when we have non-orthogonal basis, then as I told you that you have something like which I will call it as E1 cap, E2 cap, E3 cap. Let's say this is a basis, and the components of a vector, any vector A in this basis are defined as A1 E1 plus A2 E2 plus A3 E3. And these are contravariant components. Okay, and this vector is now written in terms of AI. In the index notation, we write it as AI. Contravariant components. Now the issue is that whenever you have this kind of an non-orthogonal system, then we must also have another basis. Okay, so this basis is what we call as direct basis or contravariant basis. Then you have another basis which is called, I don't know if I use this one, F1 cap, F2 cap, and F3 cap. Okay, so this basis, this A can be written in this basis as A1 F1 cap plus A2 F2 cap plus A3 F3 cap. And these are called covariant components. Covariant components, and this is called reciprocal basis. Okay, so the definition of reciprocal basis is based on this equation that EI dot Fj is always delta Ij. Okay, in the last class, I told you that in crystallography, you define this EI dot Fj as 2 pi times delta I. Okay, this factor 2 pi is specific to this crystal structure analysis that we are direct lattice or reciprocal lattice that we define there. Okay, now as I told you, it is possible to go from direct to reciprocal basis if we are planning to write down. For example, if I want to write Fj, okay, so let's say I want to write F1 cap in terms of E1. How do I write? First, I must write the component of F1 along E1. Okay, so that I will get by taking F1 cap dot E1 cap, that will be along E1. Sorry, F1 cap dot F1, right? So let me tell you. Suppose if I have a vector A and I ask what is the component or component of A along E1. If I want to get that, what I will do? I will have to dot F1 with A. So that is what is the component of A along, because F1 dot E2 is 0, F1 dot E3 is 0. In the same way, I want to write this F1 cap in terms of something into E1 plus something into E2 plus something into E3. So what is there in this bracket is the component of F1 along E1. So instead of A, I'm going to ask F1 along E1. That means this must be equal to F1 dot F1, and this must be equal to component of F1 along E2. So that is given by F2 dot F1, and this is F3 dot F1. Correct? So you can write this in the following fashion. So you want to write F1 cap, F2 cap, and F3 cap. You want these vectors. You will write this as a matrix. Okay, so that is F1 cap dot F2, F1 cap, F1 cap dot F2 cap. Okay, these are all superscripts, and this is F1 dot cap F2 cap, F1 cap dot F3 cap, and so on. So you will have this matrix multiplied by E1 cap, E2 cap, E3 cap. That means I will write this matrix as Gij, which is defined as Fi cap dot Fj cap. Okay, so this is called a contravariant metric tensor. So you can see that a contravariant basis can be converted into a covariant basis. I could have also written this Gij, the covariant metric tensor, as Ei dot Ej. This is a covariant metric tensor. So what happens is that I can write it in the following fashion. That is Fj cap is equal to Gji into Ei cap. So I is repeated, so it will be summed over, and j is free index. So this is one transformation. Other is Ej is equal to Gji Fi cap. So this is another transformation. So the basis transformation from contravariant basis to covariant basis or direct basis to reciprocal basis is always obtained by this metric tensor. Okay, so this is one concept, and as I told you that if you have an orthogonal coordinate system, your Gij will be same as Gij, and that is equal to delta Ij, because the matrix will be a diagonal matrix for orthogonal coordinate system. Orthogonal basis, because by definition, as you know, is Gij is Ei dot Ej. If they are orthogonal, this becomes delta Ij. Okay, so that is a special case of that. Now let us look at okay, so let us ask the following question. Suppose if I have, so let me ask the following. Suppose I have a vector A which is given by A1 E1 plus A2 E2 plus A3 E3, and this is indirect basis. Okay, I could have also expressed this A in reciprocal basis. That is A1 F1 cap plus A2 F2 cap plus A3 F3 cap. This is in the reciprocal basis. Okay, now I want to ask a question. What is modulus of A? What is modulus of A? Our modulus of A is basically the norm of this vector, which means it should be invariant under rotations. Right? You rotate the vector, it should not change. How do we write this modulus of A? Is it A super 1 square plus A super 2 square plus A super 3 square? Let's assume these components are real, so forget about taking mod A square. So let's say that A1, A2, A3 are real, both when their subscripts are superscripts. Is it an easy question or a difficult question?
Since we don't have an orthonormal basis, it can't be square of the components. Sum of
Correct.
square.
Correct. Yes, that is. So let's look at some simple example. Suppose I have a two-dimensional vector, and let's say I have two coordinate system. This is I cap and this is j cap. And if I have a vector whose elements are, let's say, A1 comma A2, then in this coordinate basis, if I write A as A1 I cap plus A2 J cap. Now I know that modulus of A is A1 square plus A2 square and the square root. Correct. So this is what we know if we have an orthogonal coordinate system. Supposing, let's say I have a basis. Let's look at another basis. Suppose I have a basis like this. Let's say E1 is equal to I cap and E2 is equal to I plus J cap by root. Suppose I have a basis like this. I know that this is non-orthogonal basis. That means I have a basis like this and then like this. This is I cap and this is I plus J cap by root. Right? So you know that this is non-orthogonal. So you can write this A in terms of this. Let's say I write A is equal to some A1 E1 plus some A2 E2. Now this A and A can be related because I write this A1 I cap plus A2 E is, now I know this I plus J cap by root 2. So therefore I can write this as A1 plus A2 by root 2 into I cap plus A2 by root 2 into J cap. So this tells you that your capital A1 is equal to A1 plus A2 by root 2 and capital A2 is equal to A2 by root 2. Correct? So you know, from here if I ask what is A, definitely that is not equal to A1 square plus A2 square and the square root. Correct? This much is clear from here, right? So basically it is, so modulus of A is equal to A1 plus A2 by root 2 the square plus A2 square by 2 and the square. Okay, so that is equal to, you can write A1 square plus A2 square by 2 plus 2 A1 A2 by root 2 plus A2 square by 2. That is square root of A1 square plus A2 square plus root 2 A1 A2 in the square root. So this is not this alone, right? There is an additional term here. Okay, this is the norm. Okay, but how do we get this norm? Suppose if we don't know, now that we know that this is given, this E1 and E2 are given in terms of IJK, I'm able to show you that the norm is this. But suppose if I am given some E1, E2 and I know A in terms of E1, E2, how do I find out the magnitude of A? Okay, so for that, let's understand the following. So let's continue with this example. Supposing if I have E1, so I have the following thing, right? E1 is equal to I cap and E2 is equal to I cap plus J cap by root 2. Now one can do this by simple inspection. So let's say this is your I cap and this is your I plus J by root 2. So now I want to find out F1 cap. Now what should be F1 cap? F1 cap dot E1 should be 1 and F1 cap E2 should be equal to 0. Correct? So that means this one should be proportional to sorry, it should be perpendicular to E2. Correct? So what is perpendicular to E2? You can say this one. Okay. So that is, let's say, I minus j by root 2. Okay. That is perpendicular to E2. Correct? And so, or you can do something like this also. Let's say your F1, you can write it as x times I plus y times j. Okay. Then you demand that F1 cap E1 should be equal to 1. That implies x should be equal to 1. And then F1 cap E2 should be equal to 0. That implies x plus y by root 2 is equal to 0. That means your y should be equal to minus x. So that will tell you this is the F1 cap. Okay, so what about F2 cap? F2 cap is equal to, so let's again say that xi plus yj, because x and y are unknown. So what I want is, I want F2 dot E1 should be 0. Correct? So that means what? If E1 is I cap, right? So that implies x is equal to 0. And F2 dot E2 should be equal to 1. Already y, x is 0 from here, so this is only y. So that means, that implies y by root 2 is equal to 1. That implies y is equal to root 2. Okay, so what are your reciprocal vectors? So F1 is equal to I minus j by root 2 and F2 is equal to root 2 times j. Okay, so this is the basis vector. Now we can ask, yeah. So we can ask.
Excuse
not
me,
a
sir.
unit vector. Yeah.
Sir, I have one question here. Mere collection of F1 vector and F2 vector with the special property produce a basis set, sir.
Correct.
I mean, if we collect vectors with that special property of EI dot Fj delta Ij, that itself will produce a basis set.
Yes, that's correct. By using that definition, you can find that basis. Okay. So I'm just wondering that since this has to be a unit vector, I think it is sufficient if you simply call this simply j, because this root 2 is just multiplication. But let me see whether that is important or not. Okay, so now, so we started with the premise that this A is A1, A2 into E2, right? So let's write that. So the vector A is A1, E1 plus A2, E2. Now I want to write this in terms of F1, F2. So for that, what I will do is, I know that this E1, E2 basis is related to F1, F2 basis by a matrix. F1, F2 basis by a matrix. What is this matrix? This matrix is, as you can see, when we discuss this, this one. So EJ is related by GJ. GIJ is EI dot EJ, right? So the matrix is simply E1 dot E1, E1 dot E2, E2 dot E1, and E2 dot E2. So that is equal to 1, and E1 dot E2 is 1 by root 2. This is 1 by root 2, and this is 1. So I can say that E1 is equal to F1 plus F2 by root 2, and E2 is equal to F1 by root 2 plus F2. So I can substitute that here and then write this A as A1 into F1 plus F2 by root 2 plus A2 into F1 by root 2 plus F2. So now I can write this as A1 plus A2 by root 2 into F1 plus A1 by root 2 plus A2 into F2. Okay. So now we have two vector written in the two forms, right? So I have A, vector A written in terms of E1 cap plus E2 cap. This is how we started. And then the same vector can be written in the reciprocal basis. That is A1 plus A2 by root 2 into F1 cap plus A1 by root 2 plus A2 into F2 cap. Okay. Now I want to say that, so this is what I'm going to propose. Okay. So I want to propose this scheme that I'm going to define that modulus of A is always obtained by taking the contravariant component multiplied by covariant component, A by root 2 into 2 plus A2 into A1 by root 2 plus A2. That means I multiply this one with this plus this one with this. Okay, so that is going to give you A1 square, that is mod square I am taking, plus from here I will get A2 square plus A1 A2 by root 2 plus A1 A2 by root 2. That is 2 times A1 A2 by root 2, that is root A1 A2. Correct? So this is exactly what we have seen when we tried to find out the modulus of A using that I and J, right? So whenever we have this contravariant covariant vectors, if you have non-orthogonal coordinate system, then the distance or the norm of the vector has to be defined as A J, A, J. One superscript and one some subscripts. Only the repeated indices are summed over only if they are, I mean, you will get, so it is like saying this is a vector, this is a vector, but this whole thing is a scalar because you are summing over J. This is like dot product. Okay, a dot product in a non-orthogonal coordinate system is between the components of contravariant and covariant or direct vector and a reciprocal vector. You cannot get the magnitude by simply taking one of the vectors. So if you want to even find the magnitude of a vector, you require both bases. Direct basis is required, reciprocal basis is also required. Okay, so this is an important point. I just would like to know whether you have got this or are there some questions?
So should we take this as a definition of magnitude, or is it something that we can arrive at?
I have see though, if you have non-orthogonal coordinate system, you want to produce something that's invariant of rotations. This is the only way that you can produce, and hence this becomes the definition of the magnitude.
Okay, because usual definition is square root of self inner product is the usual definition of norm.
Correct. So so this is the definition of inner product here. See, the inner product definition is not constant, right? It changes from context to context. So here the inner product always gives you a scalar. Now the inner product definition here is you should take one contravariant vector and another covariant vector.
Okay, sir.
Excuse me, sir. Yeah.
Satya, it's Kamal. Yeah. Anyway,
Yeah,
the cross terms are always zero because that is the definition of EI and FI.
Correct.
Yeah, that's why. Like if you arrive at just a dot product, you said dot product. You are taking it. No cross term will survive. Only the same index will survive.
Correct. And that's the reason why we are defining another basis, because that will not you take inner product with the same vector. So we are defining this another basis so that the cross product will give you a scalar, and then that will resemble the norm. It doesn't change with the rotations.
Yeah.
Okay, so what I'm trying to claim here is that if you say that this AJ upon rotation will become A prime J, then this AJ will go to A prime J, but that will be same as AJ. Okay, so this is invariance. Okay, so I just worked with the two-dimensional vector here, just to say, maybe if I'll just go through this once again. So I started with the definition of vectors like this one, and I said I represent this vector A in terms of this E1, E2 like this. But now since I defined E1, E2, I have first tried to represent this in IJ. Then I have this A1 is this and A2 is this. So the modulus of A I can find out as square of this plus square of this, because this is orthogonal. I and J are orthogonal. So I get this expression. Okay. Now I wanted to show you that this expression is same as you have. So you don't even have to find out F1, F2. So I have found them out, but you don't even have to find out. I use this metric tensor and write E1 and E2 in terms of F1, F2. Okay, and then substitute for E1 and E2. then I get in the basis of F1, F2, these are the coefficients. That means these components are covariant components, whereas these components are contravariant components. Now, what I am suggesting is that mod A square can be written as contravariant component multiplied by covariant component, contravariant component multiplied by covariant component. Then you will get this expression, which is same as what we derived by expressing the direct basis in terms of orthogonal basis. Okay, so that is the claim that I'm making here. Okay, so now this is good. So now, if now I'm trying to make this statement in this direction because we would like to understand these things in a very general context, but these are some different special cases. Now, another case that we would like to look at is okay. So let me put it this way: that I have. Okay, so now you know. So as far as three-dimensional Cartesian coordinate systems are coordinate system is concerned, then we have this okay, let me put it this way. So I think okay, let me put it this way. In three-dimensional Cartesian coordinate system, we have two cases. One is the basis can be orthogonal or it can be non-orthogonal. And the transformation is like rotation. We are trying to say how vectors are transformed under rotation, how tensors are transformed under rotation, how scalars are transformed under rotation, and so on. But then if you go to something like space-time, okay, in four-dimensional space-time, the transformation is different. Okay, so the transformation is called Lorentz transformation. Okay, so if you imagine that you have some coordinates, some frame of reference called S. Okay, so let's say this is X and this is T. Y and Z I'm not writing. And let's say there's another frame of reference X prime and T prime. And then this is going with respect to this frame with the velocity in this fashion. Then you know that this vector, you can write this as a 4 vector. Okay, so first component is time component, which I will write it as CT, X, Y, Z. So they will become X prime, Y prime, Z prime. And this can be written as a Lorentz transformation matrix, which I will call it as gamma minus gamma beta 0, 0. I will tell you what gamma and beta are. Gamma 0, 0, 0, 0, 1, 0, 0, 0, 0. This is for this special case where S prime is moving with respect to S along X direction. So Y and Z don't change. Where here this gamma, or first let me write beta. Beta is the velocity of the frame divided by speed of light. And then gamma is defined as this Lorentz factor, so 1 minus beta square. Okay, that is 1 minus v square by c square. So you have a Lorentz transformation matrix like this. So I can in general write this in the following fashion. So I will say that this 4 vector, I will call it as x mu. And this is something like L mu nu to x mu. So this is kind of a transformation matrix. This L mu nu is the Lorentz transformation matrix. Okay, so you can see that upon this transformation, so you can say that this x prime mu can be written as, from this matrix, you can show that this is del x prime of mu by del x nu into x nu. So this is exactly like what we have written in the previous case. In the previous case, these are related to rotation matrix elements, but here they are related to Lorentz transformation matrix element. But the general structure is same, right? So we have x prime. So this is exactly like contravariant. And if you say del prime of mu, then that will be del x nu by del x prime of mu. Sorry, this is into del nu. So this is like covariant. Now, just like what we have seen here, that if you have some x mu, and if you have a corresponding x nu, then you want to find something that is invariant under Lorentz transformations, then you must write x mu, x mu. This is like magnitude of this vector, or a scalar which is invariant under transformation. So such quantities are called Lorentz scalars. Okay, as you can see, if you write like this, we already know what is a Lorentz scalar. For example, Ct the square minus x square minus y square minus z square is a Lorentz scalar. So this is invariant under Lorentz transformations. That means if you write this as Ct prime x prime square minus y prime square z prime square, that is Ct prime square minus x prime square minus y prime square minus z prime square is equal to Ct square minus x square minus y square minus z square. So this is same. That means this quantity is invariant under Lorentz transformations. So if you say that your x mu is a vector like this, Ct x y z, right? And what should be your x mu? That should be equal to Ct minus x minus y minus z. So that x mu will be a Lorentz scalar like this. That means in this special relativity, when you have this four-dimensional space-time, the metric tensor G mu nu, or it could be a mixed metric tensor G mu nu, has this following form: 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1. This is diagonal, but all the spatial elements will be inverted, and then time part will be unaffected. So that is the metric tensor, which changes from covariant to contravariant vectors. And some familiar four vectors I can write down. For example, if you want to write a momentum four vector, P mu, which is equal to, first component is energy by C, and then you have momentum vector Px, Py, Pz. Now, if you take current density four vector, you have charge density C times rho, and then current density vector. If you have a vector potential, four potential, so you have scalar potential divided by C, and then the vector potential. Okay, so like that, you have these 4 vectors, and you can see that, for example, if I ask what is P mu, whatever is P, any 4 vector, when you write something like this, it is invariant under Lorentz transformation, right? So that is equal to, you can see that E square by C square minus P square, right? So that is your minus P square is minus Px square plus Py square plus Pz square, like that. Now this has got the momentum, and this is Lorentz invariant means what? This is same in all frames, all inertial frames. This is same. Okay, so suppose if you have a particle, so let's say you have a particle and it has certain energy E and certain momentum P, then E square by C square minus P square is same in all frames. Same in all frames. That means you must be able to write down some momentum which does not change from one frame to the other frame, right? So the only quantity that we know that does not change in one frame to the other frame is speed of light. So that should be there, a part of this expression, and we want a momentum coordinate, or momentum, some quantity which has got the dimension of momentum, in fact momentum square in this case. So you will see that the only quantity that you can construct like that is minus P square is equal to the rest mass square C square. So this gives you the energy momentum relation, E square equal to P square C square plus M square C to the power 4. So this is a relativistic energy momentum relation, which is essentially, it is like magnitude of this vector P. Okay, so this so these are some interesting consequences of writing contravariant covariant vectors, and then finding out the magnitude of a vector as a combination of multiplication of contravariant and covariant vector.